Shells and subshells. Orbitals that have the same n are said to belong to the same shell. So if n equals 1, we say we're talking about orbitals in the K shell. And then if n equals 2, that's the L shell. For n equals 3, what would be the name of the shell? Alphabetical order. K, L comes after L. M. For n equals 4, that would be the N shell. Okay. Now, orbitals that have the same n and L, we say, belong to the same subshell or sublevel. Right? And we usually use a code letter for the quantum number L. So the code letter for L equals 0 is S. It's called spectroscopic notation. The code letter for L equals 1 is P. So I've heard about p orbitals. Okay. P orbitals are orbitals for which the quantum number L is 1. Okay. S orbitals are orbitals for which the quantum number L is equal to 0. D orbitals are orbitals for which the quantum number L is 2. F orbitals, L equals 3. For L equals 4, what's the name of the orbital? What kind? What's the code letter? After that is alphabetical. And there's a letter you skip somewhere, but usually we don't go beyond G. So what's the spectroscopic notation for a subshell that has n equals 2, L equals 1? 2. What's the code for L equals 1? So you're talking about the 2p subshell. Right? So orbitals in a subshell, you specify an orbital by specifying 3 quantum numbers, right? N, L, and M, or M sub L. So for example, if n equals 2, L equals 1, M equals plus 1, you're specifying a wave function, a particular wave function that describes an electron in your atom, right? So quantum number n is 2, quantum number L is 1, M plus, we can write it as in ket notation. You can just list the quantum numbers, or you can put the quantum numbers as a subscript for psi, or you can use your code letter for L, and then so you have your n here, n equals 2, and the plus 1 here is the code, is your value for M. You specify an orbital then, in other words, you define that function for the electron by specifying quantum numbers n, L, and M. And so by a set of quantum numbers, n, L, and M defines an orbital. All right. Since M goes from negative L to positive L, there are 2L plus 1 orbitals. So for example, if you have what we call a D subshell, D is code for L equals 1. Remember, L equals 0, you have an S orbital. L equals 1, you have a P orbital. For L equals 2, the code letter for L equals 2 is D. So L equals 2. So that means your M goes from negative 2, negative 1, 0, 1, and 2. That's 2L plus 1. 2 times 2 plus 1, that's 5 possible M values. Okay? So in any given subshell then, since you're defining a subshell as all orbitals that have the same N and L, so any given subshell is going to have 2L plus 1 orbitals. There's 2L plus 1 possible combinations of N, L, and M for a given N and L. Right? So in general, then, the number of orbitals in an S subshell would be what? What's L for an S orbital? 0. So 2 times 0 plus 1 is just 1. An S orbital is the S subshell. P orbitals come as a set of how many? A set of 3. Anytime you have a P subshell, so 2 times 1 plus 1, there's 3 orbitals in a P subshell. What are those 3 orbitals? How do you make distinctions between those? You can call them PX, PY, PZ from your freshman chemistry, or you can say they have different M values, plus 1, 0, or negative 1. And if you remember when we were talking about spherical harmonics, we said if you take linear combinations of the plus 1 and the negative 1 spherical harmonic, you get the real equivalents, what we would call the PX and the PY. So you can call it 2P plus 1, 2P negative 1. and 2p 0. Okay, but instead of 2p plus 1 and 2p negative 1, you can take linear combinations and you get 2px and 2py. A d subshell has how many orbitals? 2 times 2 plus 1 equals 5. A d subshell consists of 5 d orbitals. An f subshell, 2 times 3 plus 1, 7. Okay? Now, when we say something like 2p, okay, we could mean the 2p subshell or any one of the orbitals in the 2p subshell. Right? So if you don't specify the m, if you don't specify the m quantum number when we're designating something like 2p or 3s or 3d, what we mean there is we could mean either the subshell or one of the orbitals in